So the first speaker today will be Jingyin Huang from Ohio State University, and he will talk about a geometric model for groups quasi-isometric to RAAGs.
Thank you very much for the introduction, and thank the organizer for the invitation. So this talk is going to be based on joint work with Bruce Kleiner. So I will start by remind you some basics about quasi-symmetry and the measure equivalence classification of finite generated group. So I'll start with this definition, probably most of you already know. So a map between two metric space is a quasi-symmetry. So that's if you satisfy the following two conditions. The first condition basically says F is L by lattice up to some bounded area A. And the second condition basically says F is surjective but up to some bounded area A. So the notion of quasi-symmetry basically is a cross notion of bi-lattice equivalence with some bounded area. So this notion is closely related to group theory. So let's take a finite generated group. By the way, all the group in this talk is going to be finite generated. So we can consider Cayley graph of this group respect to some finite generating set. And then this Cayley graph has a metric. We just consider graph metric where you declare each edge has length 1, and then you can look at the path metric. So this turns the group into a metric space, and it turns out that different Cayley graphs respect to different choice of generators actually are quasi-symmetric to each other. So that means every finite generated group has a well-defined quasi-symmetric type, and it makes sense to talk about asymptotic geometry of a finite generated group. And this will be a nice setting up to study the cross geometry of a group, because you see this is an invariant. So that's a natural question proposed by Gromov, is to classify finite generated group up to quasi-symmetry. So at the same time, where Gromov proposed this program, he also proposed a analog program, which is sort of a measure equivalence, measure theoretical analog of this notion. To motivate the other program, so I want to give you the following alternative characterization of when two groups are quasi-symmetric. So again, G and H are finite generated group. So they are quasi-symmetric if I can find some locally compact space X. So notice that here X is just some topological space. X is not a metric space. It does not have a metric. And also my group G and H is going to act on this X such that the action is proper discontinuous and have compact fundamental domain, and their action commutes. And the action, again, so the action does not preserve any kind of metric. It's just the action by homeomorphisms. And Gromov shows that as long as these two this criterion are met, then these two groups are quasi-symmetric. So this criterion looks a little bit surprising at first glance because it does not have any reference to a metric. However, you see that the group is closely related to the space as the action, because the action is properly discontinuous and compact, has a compact fundamental domain. Also, these two groups are closely related to each other because their action will require the action commutes. So this and basically this can be used to prove these two groups are quasi-symmetric. So now motivated by this alternative characterization of quasi-symmetry, which is seemingly less geometric, I want to remind you there's another equivalence relation called measure rigidity. It's basically a measure theoretical analog of this notion of quasi-symmetry. So here we just do the most natural thing. We replace the locally compact space by some standard measure space. And instead of have action by homeomorphism, we're going to have action which is measure preserving. And instead of requiring the action is properly discontinuous, we're requiring the action is free. And the compact fundamental domain is replaced by have finite measure fundamental domain. And then again, we want these two groups to have commuting actions. And this actually gives rise to an equivalence relation of groups. And then again, so it's natural to ask, so when are two groups measure theoretical? Measure equivalence. So these are two sort of notions of groups, which one of of coarse geometric flavor and one of measure theoretical flavor. and one can try to use them to understand various properties of the groups. Okay, so now I want to mention that just to give you very simple examples. So if one group is a finite index subgroup of another group, that they are both measure equivalence and quasi-symmetric. However, in general, if two groups are measure equivalence and quasi-symmetric, then their algebraic structure could be quite different. Okay, so now so this classification, QI classification and measure equivalence classification has basically motivated a lot of interest in mathematics. So I want to just mention one interesting result in this direction. So we take G prime to be a higher rank simple Lie group, and I take just some lattice. So just ignore this word irreducible. I just mean just some lattice. Okay, and then there's a rigidity result with respect to quasi-symmetry for lattices. So it turns out that any finite geometric group quasi-symmetric to this lattice is actually virtually a lattice in the same higher rank simple Lie group. So this is a deep result, and so this word virtually means that up to quotient by a finite subgroup or passing to a finite index subgroup, then this edge is a lattice inside the same higher rank simple Lie group. This basically is a way of saying that this structure of this higher rank simple Lie group is rigid and quasi-symmetry. And another remarkable result in this direction is the measure equivalence rigidity result by Furman. Basically, he proved that any finite geometric group measure equivalent to G is virtually a lattice in G prime. So in this case, the quasi-symmetry and the measure equivalence seems to follow the same rule, but their proof is actually quite different. And then so now, since our topic is the polyhedral product, and we've seen that the higher rank the structure of a higher rank simple Lie group is quite rigid, and both notions, the quasi-symmetric deformation and the measure equivalence deformation. And then it's naturally ask, okay, so let's take the polyhedral structure, and then how rigid is this structure and the quasi-symmetry or measure equivalence. So this will be our goal today. So we're going to focus on sort of the most simple examples of right-angle Artin group. So which is, but this example is already interesting enough, and it actually hints what will happen in general. And today my focus is going to on the quasi-symmetric, quasi-isometric side, which is more geometric. But at the end of the talk, I will also mention some comparison with measure equivalence classification. Okay, so now I will start with some basic terminology about polyhedral product. So let gamma be a finite simplicial graph, and I take V to be the vertex set of gamma. So, and then for each vertex, I'm going to associate a point in the metric space. So it's a metric space with a choice of base point. And I'm going to define the gamma product, which actually is the polyhedral product of this class of metric space, is the following metric space. So the first step, so for each complete subgraph of my finite simplicial graph, I'm going to associate a metric space, which is basically, if your vertex is in the subgraph, then I'm going to take the whole space. If the vertex is outside the subgraph, I'm going to take just the base point. So this is basically a product of some of the factors with some points. And then you see that this kind of construction give you, if you have a complete subgraph delta 1 sitting inside another complete subgraph delta 2, then I have 0 of delta 1 naturally sitting inside 0 of delta 2. And this is an isometric embedding the respective metric. And then the gamma product as a metric space is basically, I'm going to start with the disjoint of all these Z deltas, where delta are ranging over all the complete subgraph of gamma. And then I'm going to glue these Z deltas together respect to this sort of inclusion relation. And the resulting space has a well-defined metric. And this is going to be the gamma product I define. And this is also a metric space. And notice that this gamma product depends on the choice of base point. Okay, so now I recall that the Sawati complex, I defined Sawati complex to be the gamma product of unit circles. So it's also depend on gamma, because this unit circle is homogeneous, so the definition actually does not depend on your choice of base point. And then the way of defining RAAG is basically a rectangle Artin group with defining graph gamma is the fundamental group of the associated Savati complex. And we can make this definition more explicit. So it has a generator. It has the following presentation. I have one generator for each vertex of the graph. So if you trace back the construction, so each vertex gives you a circle. So here ZV is a circle, and this circle gives you one generator. And each edge of this graph is going to give you a product of two circles. It's going to give you a torus, and this torus is going to give you a relator over here. So two generator commutes if only if the corresponding vertices are joined by edge. So this is the presentation of this rectangle Artin group. And the isomorphism problem for RAAG has a very clean solution to RAAG isomorphic if the two graphs are isomorphic. So now I want to introduce a bit more terminology, which is going to be useful later. So I'm going to denote X of gamma to be the universal cover of S of gamma. So this X of gamma is going to be a Cat0 cube complex. So I should explain a bit. So let's first think about S of gamma. So S of gamma is basically a union of torus, because for each complete subgraph, I'm going to have a torus, and then it's basically a union of all these torus together. So that means its universal cover has a natural cell structure which is made of cubes. And this Savati complex has a metric which induced from the unit metric, the standard metric of the circle. And this metric turns out to be non-positive curved in some sense. So that's what, and this metric passes to the universal cover, which is also non-positive curved. So this is what this word Cat0 means. It means some notion of non-positive curvature. And this is what the universal cover looks like. And since this is the universal cover, then the group is basically the group of Dexter transformations. The action is geometric. That means the action is property is continuous and co-compact. Co-compact means the quotient S of gamma is compact, and the action is by isometry. So we think X of gamma has a natural metric. And then recall that the cliques, or that's the same thing as the complete graphs of gamma, they're going to give rise to some torus in S of gamma. So this torus, we call them standard tori. And then the fundamental group of this torus sit as a subgroup of the of G of gamma. So we call this subgroup standard abelian subgroup. And we also define standard flats in the universal cover to be the lift of this standard tori in S of gamma. And if you think about how G gamma is going to act on the universal cover, it tells you the left cosets, there's a one-to-one correspondence between the left cosets of standard abelian subgroup in your RAAG and the standard flats in X of gamma. So this is the basic setting up. So this standard flats, which come from the standard tori, is going to play a very important role in rigidity. So since downstairs, the Savati complex is a union of standard tori, then upstairs, the space, the Cat0 cube complex, is a union of standard flats. And then I should say that the intersection pattern of standard flats is going to sort of determine the rigidity of the space. So it's going to play a very important role later. So now, so here's the question we want to answer today. So basically motivated by the question, by the theorem we already seen in the high rank lattice case. So recall that we know that this G of gamma acting properly discontinuously and co-compacted by isometry on X of gamma. Another way of saying the same thing is basically says that this group is a lattice, or is a uniform lattice in this locally compact topological group, isometric group of X of gamma. So this is a group of isometries, and it has a natural topology. It's basically the compact open topology, and it just make it a locally compact topological group. And then this RAAG sit as a lattice inside this locally compact topology group, which is usually much larger than the RAAG. And then the question we want to ask, okay, motivated by just trying to make analogs to the high rank lattice result is that suppose I have another group quasi-symmetric to this RAAG, then is that group virtually a lattice in this isometric group of X of gamma? So this is the first question. And the second question we would like to ask is basically motivated by Gromov's quasi-symmetry classification. So if I have another group quasi-symmetric G of gamma, then are these two groups commensurable or not? Commensurable means that they have isomorphic finite index subgroup. Okay, so these are the two questions I want to answer today. So let's think about question one a little bit more. So the question one seems a little bit artificial if you think about carefully. So at first glance, it's a rather artificial question because what we want to do is we want to compare to the higher rank lattice case. And let's try to recall what we did in the higher rank lattice. So we take a Lie group and take a lattice. So that means this lattice canonically sit inside the Lie group. And then we ask whether other group quasi-symmetric lattice is also a lattice in this Lie group. But here, what we start is the other way around. I start with a discrete group and I stick it into some locally compact topological group. But this locally compact topological group may not be canonical. It may be just this isometric group for X of gamma seems that the choice seems rather arbitrary. So from this viewpoint, then the question one seems also quite artificial because so I can also embed, because there's many locally compact topological groups which contain G as a lattice, why I just want to study this group but not other groups. Okay, so the answer is the following. Okay, so basically, if you agree that this topological locally compact topological group is the canonical group which contains this lattice, then there's no argument. Let's say if you don't agree, this group isometric group of X of gamma is a canonical choice, and you think this is an artificial question, then that means we have to understand, or what would be, then we'll have to understand why this choice is not a canonical choice. And what would be a canonical choice if you want to put this lattice inside some locally compact topological group? And then in order to answer that question, then we have to answer question one. So because even the answer is no, then we have to start with this. And if the answer is no to question one, then it tells us, okay, so the structure is not that rigid and this group is not that canonical, and then we still have something to do. So in either case, whether you agree that whether this locally compact topological group is canonical or not canonical, then in either case, it's helpful to understand question one. And actually, in the end, so we will show that the answer to question one is actually no, but a weaker version of question one holds true. So this basically means that this isometry of X of gamma is actually some kind of canonical choice, and I will make this rigorous later. Okay, so now so let's start with this group quasi-symmetric to G of gamma. So I want to start with some standard setting up of how do you study a group quasi-symmetric to another group. So since these two groups are quasi-symmetric, so I can take a quasi-symmetry, and then each quasi-symmetry is going to have a quasi-symmetric inverse. That means it's basically a map which is a inverse up to bounded error. So I want to emphasize that this inverse may not be the set theoretical inverse. It's only an inverse in the coarse geometric sense. It's basically inverse up to bounded error. Okay, so now let's start with some nice action. So we know the action is going to act in by left action on itself, which is an action by quasi-symmetries. So the group is endowed with some word metric respect to some finite generating set. And then we can basically conjugate this left action. So we get a quasi-action of H on G of gamma. But here we got a problem here. So of course we can define this, but the composition null of the action may not hold. The problem comes from that this Q inverse is in general not a set theoretical inverse. It's just an inverse up to bounded error. So that means although the composition null does not hold, it holds up to bounded error. Bounded distance, and this is what I mean by quasi-symmetry. So what do I mean by quasi-action? So a quasi-action is basically action by a family of quasi-symmetries such that the composition law holds up to bounded distance. And I can make it more precise. So the quasi-symmetry has to be uniform. So there, and the bounded distance also has to be uniform. So this is the definition of quasi-action, and this is what we get whenever you have a group quasi-symmetric another group, then this group acting on another group by quasi-actions. So now this tells us if you want to study a group quasi-symmetry another group, then it's natural to study sort of a group of quasi-symmetries acting on another group. And to study a group of quasi-symmetries, let's first start by studying a single quasi-symmetry. So this our first step is to understand what would be that single quasi-symmetry G of gamma, and then we'll go back to study this quasi-action. So now I want to look at the regularity of a single quasi-symmetry. So now let's take a quasi-symmetry between two RAAGs. So because the RAAG is basically quasi-symmetric to its geometric model, so this chi-zero cube complex. So we can also assume the quasi-symmetry is between these chi-zero cube complexes. And then, so we have, so we want to start with some quasi-symmetry invariant to get started. So the invariant I'm going to take is a 12-dimensional flats. That means isometrically embedded Euclidean space, which are whose dimension is equal to the dimension of the space. So the reason I take 12-dimensional flats because lower dimensional flats, let's say you see that these lines in this Euclidean plane, this lower dimensional flats can be bent or can be spiraled under the quasi-symmetry. So that usually does not behave very nice. So I'm going to take a 12-dimensional flats, and my hope is that there's no room for this kind of bending or spiraling under the quasi-symmetry. And then this turns out to be true. I just take any quasi-symmetry between these two chi-zero cube complexes come from RAAGs, and then it's going to map 12-dimensional flats to 12-dimensional flats after finite host of distance. That means the image and this other 12-dimensional flats is contained in the finite neighborhood of each other. So this is basically the starting point to have some invariant to study this quasi-symmetry. And then, so now it turns out that the collection of 12-dimensional flats is actually not ideal to work with because it's not so directly related to the combinatorics of the space. So I want to pass to a collection of flats, which is the standard flats we've seen before. So this flat is sort of more closely related to the combinatorics of the graph and of the RAAG. So, and they basically come from this standard torus. And then we can ask whether the quasi-symmetry preserve standard flats or not. So the answer is no in general. So, but we can basically pinpoint what is the obstruction exactly. So here is an example. So I take G to be a free group generated by two generators. And then the universal cover is going to be, the Savati complex is basically a wedge of circles, and the universal cover is basically this tree. So let's say it's this four-witness tree where the horizontal edges are labeled by A and all the vertical edges are labeled by B. Now I'm going to take automorphism of this free group, send A to AB and B to B, and you can check this extends to an automorphism, and every automorphism is a quasi-symmetry in particular. So now we see that it's going to send this A9 to this 9, which will form AB, AB, AB. So this A9 is standard, but this AB, AB9 is not standard because our standard 9 come from cover a circle downstairs, so it can only have one label, it cannot have two labels. So this is basically the obstruction, which you already seen from the group theoretical level. And the interesting thing is that this is the only obstruction. So the theorem basically says that if there's no transfaction, so transfaction is this kind of map which send one generator to a product and two generator. If I don't see any transfaction in the automorphism, then actually any quasi-symmetry is going to map standard flats to standard flats after finite host of distance. So I should say that this low transfaction, this condition of low transfaction can be read very easily from the defining graph. So there are some criteria which I'm going to skip right now. So, and then there actually something to prove here because the quasi-symmetry is going to be much more general than the automorphisms. So here, the standard flats, they're not necessarily top dimensional or intersection of top dimensional flats. So there needs to some extra idea to pass from top dimensional to this lower dimensional thing. So not just by intersect them. Okay. So now this is the where we have this sort of nice preservation under this extra condition. So now the next step is we're going to straighten this quasi-symmetry a little bit further. So here the conclusion is we mapped standard flats to standard flats, but only after find a Hausdorff distance. I want to somehow straighten the quasi-symmetry, so I can claim that it maps standard flats exactly to standard flats, not just up to find the Hausdorff distance. So I'm going to apply a straighten process. So I'm going to do the most naive thing you might want to do. So I'm going to take a vertex in my complex, K0 cube complex, and I look at the collection of maximal standard flats containing this vertex. There's finite many of them. And then, so by the previous slides, I know that the quasi-symmetry Q is going to map each standard flats, to some standard flats, which is Hausdorff close to the image of Fi. And then, so that means we're going to associate each Fi to a standard flats Fi prime on the other side. And this Fi prime is also a maximal standard flats, and Fi prime is the unique maximal standard flats, which are Hausdorff close to the image of Fi. Okay, so now I'm going to define a map just in the zero scaling in the following way. So I'm going to send V, which is the intersection of all the standard flats, to the intersection of all these Fi primes. And then, so there's some problem with when you define this map, because the intersection of this Fi prime may not be may be empty and may contain more than one point. Then this will ruin our plan for all of strengthening the quasi-symmetry. It won't give us some nice map. However, again, so the obstruction can be read directly from the automorphism proof. You can already see from the algebraic level. So if in addition, the automorphism does not contain partial conjugation, so this is some term I'm going to explain later. And then the intersection of all this Fi prime is exactly 1 point. And then this Q bar is well defined. So this is a very nice straightening map. So let's just take this theorem for granted. And then suppose I know that the intersection is 1 point. Then basically by my construction, I know that this Q bar is going to send vertex in a standard flats bijectively to vertex in a standard flats. Basically by the way we construct it, and this kind of map is called a flat preserving map. So now I'm going to go back and explain this partial conjugation and explain why this is a natural condition. Again, I'm going to look at a very simple example. So I take the free group of 3 generated by A, B, C. And then I consider automorphism, send A to A, C to C, and B to A, B, A inverse. So this is a partial conjugation. Now you see what does partial conjugation mean? It means that you only conjugate part of your generator. And then, so now let's look at how this nothing change under the quasi-symmetry. So let's say here's my base point, and there are 3 lines, this A9, B9, and C9 passing through this base point, and their intersection is this base point. So under this map, this A9 is sent to this A9, C9 is sent to the C9, but where does this B9 goes? So let's do some computation. The vertices of the B9 is B to the I, and then the conjugation is mapped to A times B to the I times A minus 1. So that's basically, first you have to go along A, then you go B to the I, and then you go back A minus 1. So this basically means that the image is basically Hausdorff close to this B9 over here. So now you see that this 3 lines is mapped to, after Hausdorff distance, mapped to these 3 lines over here. And then it's clear that the intersection of this 3 lines is empty. So this is why we want to rule out the partial conjugation. So in general, what's the geometric intuition for partial conjugation? So let's look at this picture again. So let's imagine that we have a height function along this A9, and then B and C are in the same height. In general, the partial conjugation is going to send things in the same height to things in different height. So that's why we want to sort of rule out this kind of automorphism. And it turns out once we rule out this kind of automorphism, then all the actual quasi-symmetry is going to behave nicely, even if quasi-symmetry is much more general than the automorphisms. So now, if we put these two together, we can already have the following theorem. So suppose the auto-automorphism group is finite. So this is basically equivalent to no partial conjugation and no transaction. That's the same as the auto-automorphism finite. And again, it can be read from the defining graph. There are some combinatorial criteria. And then let's rule out the trivial case where the group is Z. Then it turns out that any quasi-symmetry can be straightened to a unique flat preserving bijection. And the straightening is finite at a finite distance from Q. So now, at this point, we can also deduce some interesting results. So it's a quasi-symmetry classification of this group. So if under the assumption find out, then these two groups are quasi-symmetric if they're isomorphic. So now this basically finished the discussion of the regularity of a single quasi-symmetry. We see that we can straighten a single quasi-symmetry, and this extra condition find out, we can straighten each single quasi-symmetry to a very nice quasi-symmetry, which maps vertices in a standard flats to vertices in a standard flats. So now let's go back to this quasi-action situation. So now we have a family or a group of quasi-symmetries. So what I'm going to do is I'm going to straighten each quasi-symmetry by a flat preserving bijection. And then, so now let's think about what happened after this straightening. Originally, it's a quasi-symmetry. That means the composition only holds up to bounded distance. However, from the uniqueness theorem of this, from the uniqueness part of the theorem, we know that up to bounded distance, there's a unique flat preserving bijection. So that means actually after you do the straightening, you get an action again because of this uniqueness result. So that means, so we can actually straighten this quasi-symmetry to an action by flat preserving bijections. So, but we are only halfway down. So it looks like it preserves a lot of structures, standard flats to standard flats, but these actions are not by isometry. Actually, they are very far away from asymmetry. So the problem is that the flat preserving map may not respect the order on which standard geodesic line. So here's a simple example. So I'm going to take again. So this is a universal cover of this figure 8. So let's imagine that this black line is a standard geodesic line. It's basically cover a circle which is labeled by A. Let's imagine that we have labeled A and known this black line. And then again, so we can draw the tree in this way. So we have this sort of branches of the tree at different height of respect to this black line. So now I'm going to define a quasi-symmetry. The quasi-symmetry only define on the zero scaling of the tree. I'm going to swap these two branches. So swap this red branch and the green branch, and fix all other vertices. And you can check that this is a quasi-symmetry, and this is not isometry. And the problem is that you see the order of points along the standard line, let's say along the standard geodesic line, black line are swapped. So the order of these 2 points are flipped. So it does not respect the order. So this is the problem of why this flat preserving map may not be isometry. So now, so the next step is I want to have a nice geometrical model. So that's what my title suggests. So I want to modify the space to take care of this sort of order flipping phenomenon. So here is the idea. So okay, so this is sort of a simplified picture of as in the previous slide. So I have this black line, and I have these two branch has been swapped, and they don't extend to isometry. So the idea is that we're going to pull this blue line and the green line away from this black line, and then connect this blue line and the green line to the black line by this sort of hinge, like this sort of two small red edges. And then now you see that if you swap them, then you just this going to extend to isometry of the space. So you just add this sort of little hinges over here. And this is sort of the idea of how we resolve flat preserving action. And then so in general, I'm going to replace each line by this sort of what we call a branch line. So we will add a lot of hinge to give some room to for you to flip around. And then I'm going to replace each standard flat by a branch flat. So basically branch flat is a product of branch line. And I'm going to glue these branch flats together in the same way as how we glue these standard flats together. And then, so this is my new space, and it's going to respect the geometry. Okay, so this is the rough idea, and now I want to make this rough idea precise, and I'm going to use the language of polyhedral product. So let's go back to the beginning. So we define the Savati complex to be the gamma product of circles. And then I define a new space, which is called the exploded Savati complex, going to be the gamma product of lollipops. So here's the picture. So I'm going to stick this point in the end. So this red edge is going to be used to arrange this kind of picture later. So we want to stick something. So this will become this kind of red edge later. So we will see. So we want to stick this edge, and I'm going to put my base point over here on the right hand side. And this lollipop has two edges. This edge in the circle we call it vertical edge, and this new edge we call it horizontal edge. Okay, and then so there's a natural map from the exploded Savati complex to the Savati complex by just collapsing all the horizontal edges. And then since we're doing nothing to the vertical edges, it's going to send the vertical torus in the exploded Savati complex, which is basically product of these vertical edges, isometrically to standard torus in the Savati complex. So now this map is actually a homotopy equivalence because we just collapse something contractible, and then you can just leave it to the universal cover. This X sub E is the universal cover of the Savati complex. And again, so it's going to map vertical flats, which are diff of this vertical torus, to the standard flats in X over gamma. So this is one way of collapsing. So my title is a double fibration. So that's basically corresponding to two way of collapsing edges in X sub E. So if you collapse all the horizontal edges, then I get X of gamma. Then what will happen if we collapse all the vertical edges? So now I'm going to still start with the same space. Instead of collapsing all the horizontal edges, I'm going to collapse all the vertical edges. That means I'm going to smash all the vertical flats into one single vertex. And then I get another map, and I get another resulting space. It turns out that this space is also a Cat0 cube complex. It actually has a name. So this is the rectangle building associated with the group. So it has a building structure. And then so by construction, the vertices of the building basically come from the vertical flats of this universal cover exploded Savati complex, because we just collapse all these flats to a single vertex. And then the vertical flats are in one-to-one correspondence with the standard flats. And then so that means we see that the vertices in the building are in one-to-one correspondence with the standard flats in X over gamma. And then so this building, roughly speaking, is going to encode the intersection pattern of the standard flats. So now let's go back to our action, quasi-action. So we see that this edge is going to acting on G of gamma by flat preserving bijection. That means edge is going to preserve all these vertical flats. However, the problem that where the action of edge is not a quasi-symmetry, because it's going to flip all those vertices inside the vertical flats. However, here, if I collapse all the vertices of the vertical flats to a single vertex, then you no longer see this flipping of order. So that means this group H actually acts on this building by isometries, because it's going to preserve the vertical flats, but you don't see this flipping of orders, because all these orders are just smashed to one point. You don't see it over here. So that means H acting on the building by isometries. So so now let's just see a very simple example of all this discussion on these slides. So let's just take gamma to be 1 point. So now what is my Savati complex? Is the Savati complex circle, and then the exploded Savati complex is just one single lollipop. And then so now the universal cover is basically this configuration. If you collapse all the horizontal edge, you got the universal cover of the Savati complex. And if you collapse all the vertical edge, you got this building, which is basically a star-like thing. And then so you see that the building is in generally not locally finite, because you collapse too much, and you actually destroy the geometry of the space. So originally it's quasi-symmetric to R, but now it's basically bounded. So you destroy the geometry. Okay. So now I think I'm ready to state the main theorem I want to tell you. So so suppose out is finite. Again, so let's rule out the trivial case. And let's start with a quasi-action. So actually the theorem is sort of more general than just have a group quasi-symmetric to G of gamma. It's applied to all kinds of quasi-action. And then we know that this rho is quasi-symmetric to conjugate, that means conjugated by some kind of quasi-symmetry to isometric action. So this is the isometric action we want of H on another cube complex X prime. So first, X prime is uniformly locally finite cube complex and is quasi-symmetric to G of gamma. So that means X prime and G of gamma has the same quasi-symmetric geometry. And the second, we know explicitly how we get this X prime. So basically, so we have this diagram. So I start with this X sub E of gamma. I'm going to collapse certain collection vertex space that I get X prime. And then if I collapse the rest of the vertical edges, I get a building. So basically, this X prime is sort of sit between the building where you collapse all the vertical edges and the X sub E of gamma where no vertical edge has been collapsed. So here is an example. So well, this would be the exploded universal cover of the exploded Sawati complex. This would be the building. And then if you collapse some part of your edge, then you get this X prime. So now you see that this is where you get these hinges where it give you flexibility to account for the permutation. And then you collapse all the rest of the edge, you got the building. So and I want to say that we cannot really collapse all the vertex. So basically, because we want this geometric model to be quasi-symmetric to G of gamma, and we want this geometric model to be uniformly locally finite, but the building is not good enough for this purpose, because if you collapse all the vertical edges, you destroy the geometry and you get a bad space, which is not uniformly locally finite. Okay. And the second thing is basically, so now I can already answer the question I raised before. So if you have an H quasi-symmetric to G of gamma, does H also is H also virtually a lattice in this group in the isometric group of X of gamma? So the answer is no, basically because there's some flipping of orders which prevent this new group to acting on the original complex. So whenever the action does not respect the order are not 9, the collapsing of these edges are necessary to make an isometric model for the group. Okay, so this is basically a way of saying that the somehow the polyhedral product structure is somehow rigid. So we don't really okay. So here's the corollary of this theorem. So suppose alpha is finite, then if a group H is quasi-symmetric to G of gamma, then basically H does not act on the original K0 cube complex, but it's acting geometrically on a K0 cube complex, which is very similar to the original one. So all you need to do is just to add a bit of hinges to take account of this this order flipping thing come from this copy of Z. So another way of thinking about this is that if you under the assumption of out finite, then the polyhedral product structure itself is rigid. All the non-rigid things actually come from Z, right? Because this flipping of orders, that's basically this lack of rigidity is lack of rigidity of Z. It's not the lack of rigidity of the polyhedral product structure. So this is another way of understanding this kind of theorem. So about what it's trying to say. So now I have a bit more time, so I want to mention some result in the direction of measure rigidity. So which is actually so in general. So I told you before that for high rank lattice, the measure rigidity result and the planetary equivalence classification result and the QI classification result has some similarity, but this is in general this is not true. So in general, these two classification of group are in general different. So it actually follows from a very difficult result of Artin and Weiss that all infinite countable amenable groups are measure equivalence to each other. For example, like the Zn. So now you see that two RAAGs, Zn and Zm, are measure equivalence to each other because they are amenable. But in the quasi-symmetric classification side, so Zm and Zn are quasi-symmetric as known as if and only if m equal to n. So you see that in general, these two classification is not the same. So, however, so somehow when the out is finite, so this is a work in progress with Camille Hobey. So we show that these two groups are measure equivalence if and only if they're isomorphic. So basically, in the special case where the out is finite, that means in the most rigid case, the measure equivalence classification is the same as quasi-symmetric classification. Is some sort of it's sort of surprising if you compare to this case over here. And okay, so I think probably I'm almost run out of time, so I'll just stop and thank you very much.
Before clapping.